the force on that electron and the force on that electron are very, very different. They actually shield that valence electron from that positive nucleus. Here we go. Coulomb's law is a relationship of force and charge and distance. And so we are talking about the attractive force between a nucleus. I'm going to draw a nucleus here for you. Well, what's a nucleus made of? Protons and neutrons, but we don't really care about the neutrons right now. So I'm going to draw some protons. And then what do we have? I've got electrons here on a level and another level and another level and so forth. So this would be n equals 1 and n equals 2 and then n equals 3 and so forth. And so we have a force of attraction, and I'm going to call that F, that attractive force, okay, between the nucleus and the electron because they have opposite charge. So let's look at our equation here. The force is equal to K, which is a constant, times Q1, and we'll say that Q1 is the charge of on the nucleus. Let's call it the effective nuclear charge. We'll get there in just a second. And then Q2 would be the charge of the electron, which basically is going to be the same for all electrons. And then what is D? D is squared on the bottom. D is actually the distance between. And so you can see that as the nuclear charge increases, that will increase the force. And then also as the distance decreases, the force will increase. So what I'm saying is this: the force on that electron and the force on that electron are very, very different. So what will cause a very strong attractive force on an electron? Two things. One would be nuclear charge and then small distance. So we're going to look at some examples that will help you process this. So I'm going to draw a couple of models for you. So let's look at lithium. He's got an atomic number of 3, so I'm going to put a +3 here. That's his nucleus. And then sodium has 11, so I've got 11 protons there. And then let's draw the electron. So I've got electron configuration. There's the level 1 and level 2. But then sodium, we're going to go level 1, level 2, and level 3. Okay, so let's drop some electrons in here. And lithium's got 2 electrons in level 1, and then we've got 1 in level 2. So that is my valence electron. I like to abbreviate VE for valence electron. And then let's go over to sodium. He's got 2 in level 1, and then he's got, let's see, 2s and 2p6. So there's 8 in level 2. And then in level 3, we've got 1 lonely electron, 1 valence electron. So I'll label that. So what we're talking about is, hey, let's compare what's the force on that valence electron for each of those. Can you see what's happening here? Well, one thing I recognize is sodium has that valence electron farther from the nucleus. So the first thing we have to do is say, well, is there a difference in the positive charge pulling on those electrons? And there is. What we're going to do is calculate the effective nuclear charge, because what's going on when we have full energy levels with electrons in them, they actually shield that valence electron from that positive nucleus. So we've got to talk about this shielding effect. And my shielding guys, let's say these are the shielding guys. Any electrons that are between the valence electron and the nucleus, those are the shielding electrons. So look at my formula down here. The effective nuclear charge for lithium is Z is the atomic number. So for lithium, that's 3. And then shielding electrons, I've got 2. So I've got a +1 effective nuclear charge. For sodium, I've got 11 protons, 11 atomic number, and then I've got 10 shielding electrons, and look at that, I've got the same effective nuclear charge. So this is what we would use in our Coulomb's law equation if we were actually calculating that. That's the positive nuclear charge that's pulling on that electron. So they're the same, and the charge of the electron is the same. So the only thing that matters as far as that equation in this case is the distance between those. And so what you see here is this one is, there is the distance there, and this one is, look at that, much farther. Okay, and so the force on that valence electron for sodium is much smaller because the distance is greater. Remember, the farther an electron gets from a nucleus, the less the attractive force.